Okay, so yeah, I'm going to talk about operator learning, and this is a collaboration with actually several speakers here today. For example, Professor Wenjing Liao and Professor Guang Ling and Professor Hayden Scheffer, and also my colleague from Hong Kong Baptist University, Hao Liu, Lulu, and Christian Moya from Purdue. Okay, so here is the outline for today's talk, and yeah, I will talk about operator learning, and I will focus on answering some questions over here. So the first question, and maybe the most important, is how can we approximate an operator, particularly using the neural network? Okay, so once we have a structure and we want to look at the performance, so particularly we will focus on the convergence and also the generalization error analysis. So once we have a mathematical understanding or some interpretations of the structure, I will talk about some algorithm designs based on the theory, so particularly some distributed learning algorithm, or you can call it splitting or federated learning algorithms. And we can use those algorithms to handle some problems, just like multiscale problems or multi-operator learning problems. Okay, so let's get started. So for the operator learning, and the idea is just to use the neural network to approximate an operator. And the operator is just a mapping between two function spaces. So I will use G in the talk to denote the operator, and the U, basically, we usually call it the input function space, and V is the output function space. So the goal for the operator learning, and we want to construct a neural network parameterized by theta. Theta is the learnable parameters to approximate the G over here. So here, the little u is the input function. So in the input function space, and this capital G operator will map this u into a function in the output function space. And we just want to use this G theta to approximate this one. So here y is an independent variable or a particular point in the output function domain. So we want a pointwise approximation. So operator learning, just similar like some other neural network work, and it was proposed around maybe 30, 40 years ago, but it didn't receive too much attention after the initial release from Chen and Chen 1993 and the 1995 paper, but it already showed a lot of success in the past 5 or 6 years in many applications. I think the major reason is just many scientific computing or scientific machine learning problem actually can be formulated as approximating an operator. So one easy example is for example, solving a PDE. So if we want to solve a PDE given the initial condition, so essentially we want to know the mapping between the initial condition, which is a function of space, and the solution, which may be just a function of space and the time. So it is very natural to formulate as a operator approximation. Okay, so there are some other applications, just like model reduction, dynamical system, and we can easily formulate in the operator way. Okay, so here at least several important works about the modern operator learning. So this one actually is the first original work about operator learning. And this one basically is some famous single deep neural operator. So just like a DeepNet, which was published in 2019, and FNO. I think maybe this was published at the same time. And the last row, some work about multi-operator learning. So I think Professor Hayden Scheffer mentioned this a little bit on Monday, and I will also elaborate on this topic a little bit. But essentially, for the multi-operator learning, one of the focus is the generalization and also adaptation. Okay, so here the icon basically is from Professor Stan Osher's group, and the pros is our work. Okay, so this is some brief history. And now let's just look at the first question. How can we approximate an operator? So, here's the motivation. So for the operator learning, the goal is still to know what is the output function. So we want to know, we definitely want to learn the operator, but it turns out what we really care is the output function. So now the question is, how can we approximate a function? So how can we represent a function? So actually, this can be motivated from many classical numerical methods. Just like a finite element spectral method, actually we are using the basis to represent function. For the finite elements, we are using some local basis, but for the spectral method or some other global method, we're using some global defined, just like a polynomial basis to represent function. So based on this, we can also propose some basis representation way to represent the output function. At the same time, we can just approximate the operator. So particularly, we have this formula to approximate the operator G over here. So here, PK and BK both are learnable neural network structures. And here, BK actually can be regarded as a learnable basis. Okay, so and then PK over here will encode the input function U and also the operator information. Okay, so this is a rough idea. And here we use this baud U. So basically that means, well, that is a discretization of the input function space or a particular input function because computer doesn't know what is a continuous function look like. And we need to consider some mesh and to discretize it. And the point on the mesh, we usually call it sensors. Okay, so the structure over here or the mathematical formulation over here actually has many benefits. And here I just want to mention something. So the first one is actually there is no discretization required for the output function. So the output function particularly is this GU, and which depends on Y. So the reason is straightforward, just because the independent variable of the output function GU, Y, so particularly this Y over here, actually is also network input. Okay, particularly is a basis input over here. So because of this, and for such kind of structure, it is not a mapping between fixed grade, or it is not a fixed grade to fixed grade mapping. So this actually will bring us a lot of flexibility in the network training and the testing. Okay, so the second point I want to mention is the algorithm, the structure here actually can be easily to be distributed, or we can learn it separately. I will elaborate on this point later, but this can enable us to handle some multiscale problems and also some multi-operator learning problems. Okay, so lastly, I just want to mention a little bit. So this is actually a very flexible framework. We can start from this approximation to develop theory for the multi-operator learning. So this is turns out, I think this will lay some foundations for the mathematical theory for the foundation model for math or foundation model for PDE. Okay, so here's some literature regarding the structures. So we have to mention the first important work by Chen and Chen, and around 30, 40 years ago. So in this seminal work, and the author actually proposed the universal approximation to the nonlinear operator G over here. Okay, but definitely this is a great work, and there is some limitation. So the first limitation over here is it is a shallow structure. Okay, so what does this mean? So that basically means both P and B neural network structure over here only has 2 layers. Okay, so but for the modern applications, if we really want to use the neural operator to solve some PDE related problem or some other problems, usually P and B structures has multiple layers. So that basically means, well, the theory over here actually cannot really give us some mathematical understanding of how we approximate and process. Okay, so this is the first limitation. And the second limitation, which is not addressed here and also in the past few years, is the performance of the structure over here. So for the performance, and I think Professor Liao mentioned this a little bit, just they have a better name, which is called the neural scaling law. And I think we focus on 2 points. One is the convergence, or basically what is how the arrow will decay if we scale up the network a little bit. Just like we have a classical numerical method, just like a finite element, we usually want to see the arrow decay if we have a denser and a denser mesh. But for the neural network, we want to see if we just expand the neural network, either deeper or wider, and then how the arrow will decay. So the secondly is the generalization arrow. So simply speaking, for the generalization arrow, it is just the average performance if we use a trained neural network to do some testing. Okay, and here if we want to do some analysis, we want to see that if this arrow will decay and how this arrow will decay if we have a bigger and a bigger training data set. Okay, so most of the study about generalization and also convergence arrow analysis are very empirical. So that basically means, for example, if we want to know the convergence, we just need to repeat the numerical experiment for many, many times. And every time we just make the neural network a little bit bigger. And then we train the neural network, find the arrow, and then turns out we fit a curve. Okay, so definitely this is very costly. And there is also some literature studying the convergence and the generalization error analysis for the structure or the neural operator, but many of them actually have a structural assumption. So that means, well, they are great work. They propose some, basically that they propose they prove the theory, but it's for some concrete PDE examples. So for example, for the elliptic operator or for some other operators. So here the goal for us is we want to make it a general. Okay, we don't want to focus on a particular PDE problems, but instead want to propose, well, if the structure can approximate some operators, but with mild assumptions. Okay, so here's our assumptions. Firstly, is for the operator, we will just assume the operator is Lipschitz. And then for the input and output function space, U and V, we will also assume it is Lipschitz and bounded with some bounded domain. Okay, so now we can just construct the structures. And firstly, we need to introduce this notation. So this notation essentially denotes a set of neural network which approximates a function. Okay, so we will use a function neural network approximation to approximate the operator. So specifically, D1 and the D2 denotes the inputs and input and output dimension. So this L denotes the depth or how many layers we have, and the P is the width. So basically, it's a for each layer we have matrix. We have a matrix, and what is the size of this matrix? And the K is the total number of trainable parameters, and the kappa is the bounds of the weight. We need to estimate this. We need to understand this, then we can just estimate the generalization error. Okay, so also another thing is the neural network within this class, they are all fully connected and basically activated by the ReLU activation functions. Okay, so once we have a neural network to approximate a function, so now we can construct a neural operator. So it has the form as before. So here AK and the QK basically belongs to separate neural network classes, and we will specify the parameters associated with F1 and F2 later. Okay, so this is some preliminaries, and now we can just discuss the first important result. So for the operator learning proof, and one key step is to establish the convergence for a functional. Okay, so later I will show you why, but for the functional, it's just a standard definition. It is a mapping between a function spaces to a scalar, function spaces to just to some scalar vector or something like this. And here the F will be a Lipschitz functional, and this U will still be the same input function space. We just assume it is Lipschitz and bounded with some bounded domain. Okay, so turns out we can use this structure to approximate the linear functional over here. So here AK is some learnable coefficients, and here the QK is some neural network structure. So basically this U, the bound U, is some discretization of the input function. Okay, so we also give an estimate of what is the size of your discretization. So essentially it is of this order. So essentially, if we want to reach the epsilon order, if we want to reach the epsilon arrow, so the size of this discretization or the mesh size should be of this order. So here the C, actually the constant C depends on the Lipschitz of the input function space, basically Lipschitz for this guy, and also the Lipschitz for the functional F over here. Okay, so this is the size of U. And then finally, the total number of parameter. And if we want to reach the epsilon arrow for this particular approximation, will be given over here. Okay, it is decomposed of two parts, and the first part is dominating, and basically, but for the second one, actually comes from we use a surrogate model to approximate this functional, and this surrogate model is built from some partition of unity, and the first part we just actually comes from using the neural network to approximate this surrogate model. Okay, so this basically is the first result, and yeah, we have some remark. So basically, if we drop out the lower order term and rewrite the epsilon as a function of this n-sharp, which is the total number of trainable parameters, And we can actually see that this result is optimal up to a log-log order to some classical lower bound estimate. But unfortunately, we don't know if there is a lower bound estimate for the functional if we have the exact same assumption. Since here we consider the ReLU activation function, but for this classical result, they actually assume the infinite smoothness assumption. So please let me know if you know such kind of result. But we actually are optimal up to this one, okay, given a slightly different assumptions. Okay, so this is the functional approximation, and now, given this result, we can move to the operator approximation. So the proof actually follows one lemma over here. Okay, so what is this lemma? So basically, remember G on U, this is a function in the output function space. So this lemma actually provides one way to approximate this function G on U. Okay, so particularly, we can approximate this G on U using the formulations over here. So here QK again is the neural network structure, and here CK is some functional. Okay, so also for CK is a functional, G is an operator. So CK composed with G is another functional. So that basically means we can use the functional results in this result to approximate this functional. And for the QK, we can construct it using the neural network easily. So it turns out we will have an approximation to the operator G over here. Okay, so specifically, we summarize the result over here, and we can see that this QK neural network structure is to approximate this guy, and this AK on U basically is the approximation to the linear functional shown over here. Okay, so so also just for the size of the discretization, this actually aligns with the previous estimate because it's just same function space. Okay, input function space U over here. And the total number of parameters behaving this way. So here I already dropped the lower order term. And, but maybe some of you are familiar with the literature. You may know that actually the lower order arrow comes from the approximation to this one. Okay, so the number of parameters estimated to approximate this one actually just a log epsilon -1. But compared to this dominating arrow, we just drop it. Okay, so this is the main result, and we also have some remarks regarding this. So firstly, there is no, we make it the assumption as mild as possible. It is not for a particular PDE, and but for a group of operators which are Lipschitz. And so no major structural assumption, no major structural assumptions. And another thing is you can see we actually have epsilon to epsilon power. But for many actually empirical work or numerical computation of the neural scaling law or the convergence rate, and the researchers usually observe the power scaling law. So I think Professor Liao mentioned this a little bit. So basically it's the epsilon to something, and this something is there is no another epsilon on top. So, but actually, well, some recent results actually show that this is, well, really hard if we don't have actual or some additional assumptions. So from some work from Caltech, and they actually show that the lower bounds actually behave as exponential to epsilon something. Okay, so that basically means if you really want to derive the power scaling law, which is widely observed in the numerical work, and we really need some actual assumptions. But this assumption, again, so we don't want to focus on a specific PDE. Secondly, this assumption should be okay for many, many scientific computing problems. Okay, so what are these assumptions? So basically, the assumptions I think we want to use more is just a low dimensional structure assumption or some finite dimensional structure assumptions. Okay, so I can show you some examples. So the first example I just I took from Professor Wenjing's talk. So essentially for the ImageNet and some papers a few years ago essentially shows that, and it has an intrinsic dimension or something like this around with dimension around 45. Okay, but for the computer vision, I think this is not the area where, I mean, just operator learning has been most powerful. And for the operator learning, I think most of the applications, as far as I know, focus on the scientific computing or scientific machine learning problems. But we also can find many examples in the scientific computing which has a low dimension or finite dimensional structure. So I can, this is one example about the multiscale. So Specifically, it's just high contrast multiscale problem for some porous media flow equation. Or particularly, this is the permeability of a Darcy flow equation. And this picture actually comes from some reservoir simulation. This comes from the real reservoir. Okay, and this problem is really hard to solve using the standard method, finite elements or some standard method, because of the dimension is really high. But some mathematicians actually show that they can create a very small set of bases, and then they can construct the solution using this very small set of bases. And later, the solution, this approximated solution actually is very close to true one, so it's a very small error. Okay, so this is actually, the work is done by my PhD advisor and with his colleagues. Okay, so based on those examples, and now we just want to add one more assumptions, and this assumption is just a low-dimensional assumption. We want to assume the input function actually can be represented using a finite set of bases. Okay, and the dimension is just equal to BU. And given this assumption, and we can rewrite the proof, and it turns out we have the arrow. And this arrow essentially will behave in this way. So this N sharp basically is the total number of parameters, and this is just a standard power scaling law. Okay, so this is about the convergence, and the next thing I want to talk about basically is the generalization. Since if we want to derive the generalization, so basically we estimate the bias and the variance, and to estimate the bias, one of the necessary results is just a convergence result. Okay, but what is generalization?
Just a quick clarification. So in your previous theorem, the U you have is continuous or discretized?
Which U? This U, right?
Yeah.
Okay, so this is a good question. So U, the assumption on U is Lipschitz. Okay, but if you want to use neural network to handle a function, you have to discretize it. So
the previous theorem is for the continuous.
No, it's for the Lipschitz. Here we need to assume U is Lipschitz.
But the input of the neural network is discretized.
Oh, after you discretize it, will be some discretized value.
But that soup you are taking is AK and QK. AK is a neural network.
Yeah, so you can say, yeah.
So AK, QK, and neural network. So input of the AK is still discretized.
Yeah, this is a discretized value. You can say I use a bald U. So it's already the discretization of the Lipschitz functions.
But that soup you're taking is continuous.
Yeah, but yeah, so this, once you have U, and then if you consider the discretized version, we just didn't change it. You can just write as a bald U belongs to some space and take the soup, but for simplicity, we just take the soup over the original space this U comes from. Okay, thank you for your question. Just stop me, and if you have any more questions. Okay, so let's go back to the where we are. Yeah, here. So for the generalization arrow, basically is the average, the testing. So for example, we have a training neural operator. We use it to make the prediction of testing samples, and we take the average. So this is roughly understanding. And mathematically, we will define it in this way. So we have several expectations. So the first expectation basically is over the training data set. So here S is the training data set. And this expectation essentially determines the performance of this G hat. So G hat, we assume, is the optimizer of the training data set. Okay. So, and the other two expectation actually is for the testing samples. And this is something which is different from the previous literature about function generalization error analysis. So particularly, you can see we have one more level of randomness. So for the classical work about function generalization, we just need to consider the point sampled from the domain. But for the operator learning, we start from a function, so we need to basically first sample the function. So this will make the proof a little bit different. Okay, so here is just the summarize the results. And basically, this N denotes the number of training functions. And the NY basically denotes of the number of points we know per given functions. Okay, so this is something different from before. So because for the operator learning, we know the function, and given the function, we cannot assume for every function we know every point. Otherwise, this doesn't make sense to us. We can only assume we know the function value at a certain point, and this is denoted as NY. So finally, we show that the generalization arrow essentially will decay as a product of n times ny. And the result over here, we are already taking into the low-dimensional structure assumption. And we can also, if we drop out this lower order term, so you can still see observe the power scaling law. And this result actually, just a power scaling law decay for the generalization arrow was, I think, first observed in the first DeepNet paper in around 2019. And here we just gave some theoretical justifications for such kind of phenomena. Okay, so this is everything I want to talk about the theory. And now, given some mathematical interpretation of the structure, and we can design some algorithms to handle some problems. Okay, so particularly the algorithm I want to discuss is the distributed learning algorithm. And the problems, firstly, is the heterogeneous data set challenge, and another is just multi-operator learning problems. Okay, so let's first look at the heterogeneous data sets or the multiscale problems. Okay, so what does this mean? So basically, this means data sets contains samples presenting very different properties. Okay, so I don't know what is the definition for the computer vision, but for the mathematical application of machine learning, this is very easy to understand. Just like we have different PDE, and the PDE presenting very different property. You have a diffusion process, maybe very smooth and converge to the steady state. You may also have conservation law. It may present a shock, which has a lot of discontinuity and move to the future in time. So this is one easy example to illustrate the heterogeneous data set. So you can see we have 4 functions, and 2 of them are very smooth, and 2 of them has a peak, which is not that continuous. Okay, so well, if we want to use a single neural network structure to handle all the functions over here, okay, so what is the challenge? So that basically means we need to accommodate the function with the worst property. So particularly this guy. Okay, so that means if these functions are our input function, we need to consider a very dense discretization in order to capture this, this particular signal. But you can see that this very dense discretization actually will be an actual computational cost for this very smooth signal with maybe just very low dimension. Okay, so ideally, so different functions should be handled using different sides of the mesh. Okay, but you may have a question for this. The question is, why not we train separate neural network, one for the smooth one for the complicated one? Okay, so the answer actually is over here. So basically, I think this violates one principle which is very important in the scientific machine learning, which is data diversity. Okay, so what is data diversity? So data diversity essentially is for the generalization and adaptation. So here, generalization, I mean, just given a training neural network, and this neural network can be generalized to predict some unseen sample which is different from the training data set. Okay, so or it should have some extrapolability. Okay, and then later, what is the adaptation? So that basically means, well, given a new trained neural network, and this neural network can be rapidly adapt to the downstream task or some task which is different from the training very quickly, and also with as limited data as possible. So basically the data diversity here, basically the importance is basically if a neural network trained with heterogeneous data set, and they usually present more generalization and adaptations than the network trained with the data only contains a certain type of data. Okay, so that's why we still want to consider everything together, and but still we want to see that we can just train it separately. Just try to make sure about the network can handle functions with different properties, but efficiently. Okay, so here are some reference about data diversity, and the first and the second one essentially is actually our work, and from mainly is done by Dr. Sun from Johns Hopkins. And this one is very interesting, and essentially they show that the importance of data diversity in some real large-scale scientific applications. Okay, so my message is actually we can do this based on how we approximate the operator. Okay, so let's look at this approximation for one more time. So essentially, this is target operator, and we use this one to approximate this guy. Okay, previously we mentioned that this BK can be regarded as a basis for the output function. But one more level of observation is we can see that this bky actually is independent of u over here. Okay, so that means no matter what our input function u is, the corresponding output function will be represented using the same set of bases or particular learnable basis bk. Okay, and then for the coefficient over here, for the basis, this definitely will contains the operator, just the input function information. It will encode it and also encode the operator. Okay, but this will actually motivate us to split the learning of pk and bk. Okay, so turns out we can have two separate updates. And let's first look at the update on the right-hand side. We call it a global update. And what is a global update? So basically the goal for the global update is to update the parameter shared by everybody. So specifically, it will be the bk structure over here because the basis is used for everyone. And also during the update, we will use all the data. So no matter if your basis comes from the parabolic equation, comes from the conservation law, or comes from some other equation. Okay, so this is a global update. And then we have the local update. So what is the local update? So the goal for the local update is to update the parameters of the network specifically to a group of functions. Or if we check the formulation over here, so basically for different u functions over here, we can use different neural network to encode this u. Okay, so that basically means, well, if you have a very good easy functions, and we can just use some simple neural network with some specific dedicated activation to handle it. And if you have complicated functions, we can have a deeper neural network and with also some specific dedicated activation to handle it. Okay, and also during this local update or to update some dedicated structure, we will phrase the global parameter. Okay, so this is a rough idea, and here we have the pseudo algorithm. So so for this pseudo algorithm, we first define the task. So this is a very easy idea. So one task basically is a sub data set, and the functions will be handled using this functions in this sub data set will be handled using the same networks. Okay, and then for this algorithm, the main loop basically is the loop number 2, but this is just a standard optimization step, and you can consider some complicated one. And in this update, we have two major updates. One is the just global update, and another is for the local updates. And for the global, we update the shared parameter, and for the local, we will update the network parameter one by one for each task. Okay, so this basically is the algorithm, and we actually use the terminology from some classical federated learning paper, just a fed average by McMahon in 2016, but just like a global local task. But actually here we just want to give a very quick comment. The algorithm is fundamentally different from the fed average. Since for the fed average and the local model is updated through the local model is updated through the broadcasting of the global model. And for the global model, it is updated through the synchronization of all different local models. So it turns out there will be data transmission and also model transmission between the local and the global servers. But for our algorithm, we name it D2NO, so actually we don't have such kind of model transmission, so it is very efficient. Okay, so another thing I want to talk about, I have very limited time, but it's about cost and mathematical verification. So for the cost, well, one of the questions some people asked me before is about the number of parameters. So just the reason is, well, we actually have multiple copies of the network and one for each sub-data set. So it looks like the total number of parameters actually is much higher than we train the same data sets using a centralized neural network directly. However, I think here the dominating cost actually is the gradients-related calculation. So particularly it's just the backpropagation and the forward passes. And here we can easily estimate the total number of gradients-related calculations. So the first row over here is the D2NO cost or the method cost. So the first part is a global, second part is a local, but the calculation is the same, just the total number of samples times the cost per sample. Okay, so now if we assume, well, each local task, the cost per sample is the same, or all the local network structure are identical, the same activation, same structure, and same learning rate, everything is the same. So it turns out our cost will go back to the standard cost over here. Okay, or we have a single structure and train all the data directly without any trick. Okay, but actually we can save some actual costs. The reason just because we don't have to accommodate the particular functions as if we train everybody together. Since if we have basically this bottleneck, and if we train everybody together, we need to consider structure which must handle the most tough one. But here we can use dedicated structure. So it turns out the total cost can be lower than the training everything together. Okay, I will show you one example very quickly. But essentially, also we have some theoretical verifications. So essentially, here is the simplified case. We only consider we have two different U1 and U2, different two tasks, and they all map to the same function space. And essentially, the theory over here is we have dedicated neural network PK1 and PK2, one for U1, one for U2, and also a shared structure BK as a basis, and their combinations actually can approximate each operator separately. Okay, so this is the algorithm and some theory, and this is basically the numerical example. I think I'm supposed to finish in 2 minutes, right? Okay, okay. Yeah, but if you trust me, so we have a lower error and lower computational cost. Okay, so another application I will finish in 1 minute. It's just about multi-operator learning. And for the multi-operator learning, essentially it's just a single structure that can approximate multiple operators simultaneously. Okay, so the goal or the benefits, we actually discussed this a little bit, just for the better generalization and the better adaptations. Okay, so for most of the very famous models, just like the IPAM model and many other models, I think they share one thing in common, which is they are transformer-based model. So now the question is, can we just using some algorithm, but this algorithm can enable a single, very simple deep neural operator, just like a DeepNet or something like this, to be a multi-operator learner for the better generalization and adaptation. So this actually can be done. The easiest idea behind this is just we can switch how we do the distribution. So for different output, remember for the operator, the key is the output function is different. So basically, if we, that is actually go back to the basis over here. So essentially, we can make the basis dedicated and share the others, and then we can solve some multi-operator learning problems. So here's some example, but I want to skip, and this is some summary. And basically, we just talk about operator learning. Okay, so here are some references, and thank you.